One of the first issues that I came across when working on the robotic arm project had to do with the actuation of stepper motors. I was using the A4988 stepper motor driver, which are extremely common in hobbyist projects. However, I couldn't find any resource online or any code that explained how to achieve constant acceleration for the stepper motors. So I decided to solve this problem myself, and I found a way to do it. And that's why I'm making this video, to share with you in case anyone else has the same issue that they want to solve and don't know how to approach it. I tried to section this video into different sections. The first one will be talking about a simple implementation to achieve some sort of acceleration. That method is shown in several other YouTube videos and other forums. However, the second part of the video is completely novel, came up with me, and that's going to be how to achieve constant linear acceleration. So without further ado, let's get started. So the first method that I'll be showing you guys is a very simple way to achieve some sort of acceleration. And this acceleration will not be linear acceleration, but if your application doesn't require linear acceleration, this could be a very simple way to implement some sort of acceleration. So the stepper motor driver that I'll be using is the A4988, and it's very similar to a lot of the lower end stepper motor drivers. If you have something completely different or it's very expensive, chances are it might have some sort of angular acceleration implementation in it, or a different way to drive it, in which case these methods may not work. So I'll show you guys how this stepper motor driver works. What you do is you send it pulses, and every time the stepper motor driver sees a rising edge, it will step the stepper motor by 1 step. And that's just a single fixed angle. That's a terrible arrow. But basically this angle is a step. I'll call it theta. And for my stepper motor, this theta is equal to 1.8 degrees. Might depend on your stepper motor what yours is. And so this is how you control the stepper motor, and this is how the A4988 works. So what you see, this series of pulses are happening at a constant frequency. So what you get is a constant angular velocity with no angular acceleration at all. And you can kind of see how if we want angular acceleration, we would have to decrease the pulse width. Sorry, not the pulse width, but the distance between the pulses over time. I drew this terribly, but you can probably see that the distance, the time delay between the pulses here is larger than here. And we want this to slowly change over time. And that will achieve angular acceleration. So one easy way to do this is just to have a for loop and decrease the time delay by a fixed amount every single time. So for example, let's say that this was 6,000 microseconds, and the next pulse we would just delay it, and maybe that will be 5,995 microseconds, and every subsequent pulse we can just decrease by 5 microseconds every single time. And this 5 microseconds is a arbitrary value. You could make it 1 microsecond, in which the angular acceleration will be smaller. And this is very easy to implement in code, so I'll be showing you guys. It's just a for loop, and you just decrease it every single time. And I'll show you guys a video of how it looks in the actual stepper motor. But before that, I'm just going to show you guys the caveat with this method, and that's that the angular acceleration is not constant. And you will be able to see this in the video of it actually running. But what happens is the angular acceleration is very minimal at the start, and towards the end you will see a sudden increase in angular velocity. And if you wanted to look at the math, angular acceleration is equal to the change in angular velocity, yeah. And then in this example, let's call each of these time delay. So that's just TD, and then we can say that the change in angular velocity is equal to your theta divided by this TD minus some sort of constant. So in this case, the constant would be 5 microseconds, and that's just arbitrary, minus the same theta divided by regular old TD. So that's angular acceleration. And as this term gets smaller and smaller, as your time delay reaches, gets smaller, closer to the end of the acceleration cycle, this will go up very fast, this term, just because the denominator gets very small and closer to 0. It won't reach 0 just because you can't have let's say the stepper motor step every 1 microsecond. That's impossible. So there's a limit to how much this can decrease to, but up to a certain point, this will be getting larger and larger, and this term will get larger much faster than this term will be. And so overall, your acceleration will have a huge spike near the end of the acceleration. So I'll show you how to implement this in code, and then we'll see it in action. Okay, so over here is the code. I just quickly coded this up with the new Arduino IDE, the 2.0 beta version that just came out, and I have to say it looks so much better than the old Arduino IDE, which was really out of date, so I'm very glad they did that. The code is very simple. I'm only defining 2 pins, the step pin and the direction pin. The step pin is the pin that you want to send the signal to every time you step the stepper motor by a single step. And the direction pin is only useful if you want to change the direction, which I'm actually not doing in this case, but I just set it just in case. And then in the setup, I set both the step pin and the direction pin as output, and I set the direction pin to high, which I believe corresponds to a clockwise rotation, but I could be wrong. We'll see when we actually run it. And in the loop, we first set the stepper delay to be 3000, and this eventually will be 3000 microseconds. And so over here we have a for loop that basically steps the step pin, and delays it by whatever the delay is. So it starts off at 3000 and then returns it as low and steps it by 3000, waits 3000, and then when we're done with the loop, we subtract 1 from the stepper delay. So the first time you run it, it'll be 3000. The second time you run it, this will be 2999. And this minus minus is just the same thing as stepper delay is equal to stepper delay minus 1. That's just a shorthand. And other than that, we run it 2,300 times. So by the end of this for loop, it will be at 700 microsecond delay. And I experimented, and this seemed like one of the faster speeds that the stepper motor that I have can run at. And then after this is really unnecessary, but I just wanted to continue going at a constant velocity for the last bit. So it accelerates from 3000 all the way to 7000, and it continues, 700, and it continues at 700 for the remainder. I set it for 2000 steps, and then it stops for 1 second. So let's upload this code and see if it works. So I think it's, yep. So it compiles it and it uploads it, and let's check it out. Alright, so I just loaded the program onto the Arduino, and the stepper motor isn't running just because I haven't connected the power supply yet. I just want to mention a few things. This electrical circuit that you see in front on the breadboard is a lot more complicated than it should be, just because I was testing a bunch of other stuff on the breadboard just a while ago. And I'll try to put an overlay on this frame actually, showing you the electrical schematic. There's a website, How to Mechatronics. They did the great diagram, and I think you should be able to follow that and connect everything the way that their diagram has it, and you should be fine. As in our program, we only had to connect step pin and the direction pin. Actually, the direction pin is kind of unnecessary if you want to omit that. And no microstepping. So let's hook up the power and see if everything performs the way we want it to. Okay, so it's just ending the last segment. So that was the 1 second pause, and it's starting off very slow. Let me see if it's in frame. Okay, you guys can see it. And over here, it speeds up very, very fast. And then for the very last bit, it's traveling at a constant angular velocity. So I'll just play it again. Right, and so we can tell that the acceleration feels very non-linear, and this is if this works, then for your application, by all means go ahead and you can implement it this way. But in the next segment, I'm going to talk about how to do constant acceleration. So I'll just play this on one more time, and all right. So now let's take a look at how to achieve constant linear acceleration on a stepper motor, and this will probably be the method that I'll be implementing on my robotic arm project, and it's a little bit more complicated, involves a little bit of math, but not too bad. So let's get started. The first things we needed to find, just make sure we understand a few concepts. So first things is angular velocity. So the units for angular velocity are radians per second, and we can say for our stepper motor, I'll just draw one over here, that, say this is the start, and that's theta. We can say that angular velocity is equal to the arc length of a single step, so this is that angle, which is theta, of a step, and then divided by the time delay. So we talked about time delay in the previous part. This is the same thing. So this is the time between a pulse. And that's just angular velocity. Now the other thing we have to talk about is angular acceleration. And by definition, this is d omega over dt, which you can say is the change in angular velocity over the change in time. And that's just, the change in time is going to be the td, essentially. So we can simplify that saying that change in omega over the time delay. And we can rearrange that for change in angular velocity. So that's equal to acceleration times, times time delay. And what's neat about this is the acceleration is kind of arbitrary. It's a constant, and since we're using constant linear acceleration, so I'll write a alpha c. So this is just a random number that we set. And time delay, we know the first time delay. So how this program is going to work is we're going to tell it the first time delay, and it should be able to compute the next one. And then during the next step, it'll just take the next one and compute the third one, and then use the third one to compute the fourth one, and so on. So this is it's called a recursive function, and we just need to give it the first one. So these two are basically all known, at least for the first step, and it should be known for the next steps after that. So the third thing that we need to know is, well, change in omega is equal to, let's say, omega 2 minus omega 1. the next one minus the previous one, which hopefully makes sense. And since we defined up here, we can say that change in omega is equal to theta s divided by td2 minus theta s divided by td1. And td2 and td1 are just the next time delay versus the previous time delay. And based on this, we can believe we can simplify this. Yeah, we can rearrange. And so let's say we know td1. That's the first value we give it. And we want to solve for td2. We should be able to rearrange for td2. So td2 is equal to theta s, think over change in omega plus theta s divided by td1. Okay, so now we have a function of td2 in terms of td1, which is kind of what we need. We still have this delta omega term, but we actually solved it up here. So the final, let's combine everything. So combine, and our final equation should be td2 is equal to 1 over, so this is theta c, oh no, sorry, our alpha c, which is constant angular acceleration, times td. So this td will actually be the first time delay, and then plus theta s. Oh, why did I put 1 here? No, this is theta s, and then over td1. So that's the entire equation. And what, and this would be the answer actually. What I'm actually going to do is, since I know that theta s, which is the step that it takes, oh, let me go up a little bit more. So this is the step that, the arc length of a single step, that and the constant acceleration term are linearly related. So if you, let's say, multiply the, you can conceptually kind of see that if you double each step, well, the arc length for each step, you'll basically double angular acceleration, since it's constant. And I want to absorb the angle into the acceleration, just because to me the angular acceleration constant is an arbitrary number. I'm not actually trying to solve for a particular radian per second value. If you do, stick with this one. It's actually the better solution probably. Let me make a little box. Oh, here it is. So yeah, this is the solution that you probably want. For me, I'm just playing around with the constant acceleration term, so I'm going to use the equation td2 is equal to 1 over ac times td1 plus 1 over td1. And this is, it's the same thing. Just I'm going to have a different angular acceleration term than if I were to do it this way. But I'm playing around with it, see what type of acceleration I want, so I don't really care. So now let's take a look at the code and see how I programmed this. Here is the code that I wrote for the constant acceleration, and I'll preface this by saying that I wrote this quite a while ago, and this actually has microstepping, but I'm too lazy to change it back to without. I have to change some other constants and play around with it. So we're just gonna ignore the microstepping parts. Compared to the other acceleration, a lot of them is the same. The step pin and the direction pin are defined. These are for microstepping. There is an LED. I was just for debugging stuff. So here is when we get to the important parts. Wait time is what I called the time delay. So I initialized this with a 0.003 value, which is 3,000 microseconds. If you read this as milliseconds. And we have an acceleration term that is arbitrary, and I defined that as 4,000. So this is the number that I played around with, and 4,000 was one that I guess I felt looked pretty smooth, or achieved a constant acceleration speed that I want. And then there's a rounded wait time, which I'll get into later. I'll try to put a picture of the formulas that we just created in post-processing so that you can see a side-by-side comparison. Over here, the pin modes, the important ones are just step pin and the direction pin again. The rest of these are all micro-stepping, and there's one line about the LED. Here is the important part. So I created two functions, and these two functions are basically the implementation of the final formula that we derived. One is for positive acceleration, and one is for negative acceleration, aka deceleration. So the first one, positive acceleration, it takes in the previous wait time, and it spits out the next wait time, essentially. And all of this is just the code of the formula. So we have a change in velocity, that's the delta omega term, and that is, we derive that as saying that's TD times the acceleration term, and this is just the final formula, TD2, this is TD2 essentially, and that's equal to 1 divided by delta omega plus 1 over TD1. And I just have another clause here saying that if this is too small, set it to the minimum amount. So this is a very minimum TD that we can have before we reach the limits, the physical limits of the stepper motor, and return the wait time. One really cool way, one cool thing about the method that we did is the same exact formula can be applied, just in reverse, for the deceleration phase. So the only thing you have to change is you have to multiply the acceleration by 1. You don't need to change any other formula. You just have to say that it's the negative acceleration, essentially. And the reason why you can do that is because it's a constant acceleration. If you accelerate it at positive 1 radians per second, you're applying the formula, and if you're using a negative 1 radians per second, you apply the same formula. So it's a really neat thing that is special to the way we derived it. And here is the loop. Set the direction, and I accelerated it for 3,000 steps. And it only actually takes 1984 steps, 1984 steps to reach the maximum acceleration, which is defined by the wait time over here. But since it caps, if I say, I wrote a clause saying that if it is under, set it to this number. This is the minimum amount. So after 1984 steps, everything after that will be a constant velocity. It capped out. And so basically this part will accelerate it for 1984 steps, and then the remainder steps will be constant velocity. So we should see it to accelerate, keep steady, and then I decelerate it all the way to the very minimum as well. So that takes 1984 steps. And accelerate, keep a constant speed, decelerate, and then a delay, just so we know it finished a cycle. And that's the code. This code, and along with the previous code, I will include a link to the GitHub repository so that you can play around with it, try it. If you want to do some other microstepping, or if you want to remove it, you can do that. And yeah, so let's run this code and check it out. It should feel a lot more smooth than the first one. So compiled and uploaded. Perfect. Okay, so we just uploaded the constant acceleration program. The wiring is the same as before. We're just using more of the actual wires this time. I'm not going to go through that again. So let's just connect it and see how it works. Okay. So over here you can see that, I mean, it is a faster acceleration constant, but you can see how it's a lot more smoother. It accelerates and decelerates at a constant rate. I mean, it's a little hard to tell, but honestly, if you feel it and hear the sound, you can feel that it's a lot smoother than it was before. Yeah, it feels a lot more natural. All right, so that concludes this video. I hope that you enjoyed it and learned something from it, and I'll see you again next time.